I sometimes just think about the sheer overwhelming complexity of the universe. I mean, if you try to map the movement of every single electron in just a tiny piece of metal, not just its position, but its entire quantum state, you're dealing with an equation so vast, it's basically impossible to solve.
It really is. The world's supercomputers would take billions of years. It's the definition of an intractable problem in physics.
Okay, so let's unpack that, because that exact computational roadblock is why the Kohn-Sham equations are, well, one of modern science's greatest shortcuts.
Oh, absolutely. A complete game changer for understanding electron behavior in materials.
Today we're diving into a moment of pure intellectual genius. Our mission is to understand how this Schrödinger equation of a fictitious system actually works and why it was so fundamental it earned its creator a Nobel Prize.
It all starts with a central breakthrough, a realization that we don't actually need to track every single electron.
Right, we just need to know their density.
Yeah.
The probability of finding an electron at any given point. Why is focusing just on that density so important?
Because what's fascinating, and this is the core of density functional theory, or DFT, is that the properties of any chemical system, its stability, its reactivity, all of it, is entirely determined by that electron density.
Wow. So if you know the density...
So they know the material.
So instead of wrestling with that impossibly complicated reality, they just invented something simpler.
Precisely. They introduced the concept of a fictitious system of non-interacting particles.
A fictitious system.
Yes, and this simpler system is specifically built to generate the exact same electron density as the real complex system.
So you solve the simple system, and because the density is the same, you get the properties of the complex one.
Exactly. It's an ingenious approach. It was introduced by Walter Kohn and Sham back in 1965, and it led to Kohn's Nobel Prize in Chemistry in 1998.
That's just an incredible level of intellectual simplification, taking something impossible and making it solvable. This ability to find elegant solutions to overwhelming complexity, it's key everywhere, from fundamental science to business challenges, which actually brings us to our sponsor. This deep dive is brought to you by Embersilk. If you need help with AI training, automation, integration, or custom software development, Embersilk can help. They specialize in uncovering where AI agents could make the most impact for your business. So if you're looking to cut complexity, check out embersilk.com.
So let's look at the math behind this.
Okay.
The goal is to calculate the total energy, which we call an energy functional, AE or.
Okay, and that functional has 4 key parts, right? 4 types of energy that add up to the total.
That's right.
We have the kinetic energy of those non-interacting particles, the energy from the external potential, so that's like the pull from the atomic nuclei,
Yeah.
and then the simple electrical repulsion between electrons, the Hartree energy.
And 3 of those terms are exactly solvable. We have standard formulas for them. But the 4th term, that's where the magic happens. The exchange correlation energy, or MU.
And this is where it gets really interesting. That ESD term is the only unknown part that needs an approximation in the entire approach.
It is. We've managed to bundle all the hard physics, all the subtle quantum weirdness, the self-correction, the spin dynamics into this one single term.
So it's like a quantum correction factor.
It is. Since the fictitious particles don't actually interact, ESD has to account for everything that's missing from that simple model to make its density match the real one.
And because it's the only part we have to approximate, it has launched, decades of research into finding the perfect formula for it?
Decades. An entire field of study, really.
So what does this all mean for us, for the bigger picture? By making smart approximations for this one term, scientists can now accurately model millions of molecules.
It's incredible. You can screen thousands of potential designs for, say, new solar cells or more efficient battery components, all on a computer. It drives enormous progress.
The ability to model the universe by finding these clever mathematical shortcuts, replacing a messy reality with a perfectly crafted fictitious system, it just shows the incredible power of human ingenuity.
It really does.
That quest for deeper knowledge and elegant solutions, I find that so inspiring. It gives you great hope for the future. If you enjoyed this deep dive, please subscribe to the show. Hey, leave us a 5-star review if you can. It really does help get the word out. Thanks for tuning in.